Okay, so we're going to go through the second module here in electronics, rectifiers and battery chargers, part B. So we did talk about the back-end theory on diodes, how they work with our PN junction, and the difference between being forward bias and reverse bias, which is important when we talk about rectification, because we have an AC supply and we're potentially only going to get some of that supply through because this is only going to conduct through half of the cycle, based on the fact that the polarity changes. So if the polarity is continually changing around this diode, it's conducting, then not conducting, conducting, then not conducting. Okay, so we'll see the effects of that here in the pictures and stuff, and in the output that we'd actually see for our calculation. Okay, so I'll go through all these calculations again. I'll review this stuff before lab, so we have an understanding before we hook these circuits up. So single phase is the first one we're going to talk about. Single phase, this rectification's again the process of turning AC to DC. That's the whole point of rectification, is I need DC, but I only have an AC supply, so how am I going to get DC out of this? So when DC power is required, it's usually rectified from an AC supply. A rectifier is a device that changes AC to DC, two types, half wave and full wave. In half wave rectifiers, every second alternation is applied to the load. For full wave, every AC alternation is applied to the load. Most common rectifiers include single phase half wave, single phase full wave center tapped, and then single phase full wave bridge. And then there's three phase ones, the half wave three phase and the full wave three phase. So we're going to start with the single phase and at the half wave, and we'll just kind of build as we go. So the single phase half wave rectifier is the simplest rectifier. So it just has one diode in series with the load. So here's our AC supply on X and Z, and then we have our load again hooked up from Y and Z. Okay, and again it depends on the supply coming in when this guy's going to conduct. But our load is only ever going to see DC coming out of here. So that's what it says here. The volts out is voltage DC. Okay, so during the first alternation, okay, so when we're thinking of our sine wave, so the first alternation is that peak to max on our positive end. The X would be positive. So X is positive here with respect to Z. So then Z would be negative, bringing that negative all the way through. If we were just looking at the diode, this would be positive, this would be negative. At this point, since the diode D1 is forward biased, current flows in the circuit and voltage appears across the load. But again, just the one alternation of voltage is going to go across to see the load. Again, think of this as a split second in time here that we're talking about. One cycle is what we're talking about right now. And more specifically, the first alternation of that cycle is going to go through to the load because this diode is forward biased. During the second alternation, polarity here switches because it's an AC supply. So now I have a negative here and a positive here. So now my diode has a negative on this side on the anode and a positive on the cathode. So now I'm reverse biased. So then there's no current flow. So basically what I get is this scenario here. Okay, I'll go back to that other slide too, but just to kind of show what we're talking about. So here's the full cycle, the full 360 degrees. What it's saying is we're only going to see, when the diode's forward bias, we see one alternation, and then for this alternation, it's being blocked, okay, because that diode's acting as an open switch. So my load is going to see this alternation, then nothing, then this alternation, then nothing, and so on and so forth. Okay, so that's how this diode in this circuit now can create a pulsating DC output because we're not allowing that second alternation to come through. Again, because it's reverse biased. Okay, so just a larger diagram of what we were just talking about. Again, I usually do this stuff on the board too. But we mark the polarity, okay, on the first alternation, positive here, negative here, allowing that alternation to come through, forward biasing the diode. Then on the second alternation, it's reverse bias and does not let anything go to the load. Okay, so what this graph is showing here is the supply voltage. So here's our full supply. This is what the load is seeing. So the load's seeing when this is forward biased here, reverse biased. Forward biased, reverse biased. Now what the next part is saying the voltage across the diode. Because we've got to remember too, when it's reverse biased, okay, so it's forward biased here, this is the diode we're looking at. So here's the supply, here's the load, and this is the diode. So when the diode's conducting, we don't see a voltage across it because it's like a closed switch. If you put your meter across a closed switch, you're going to read 0 volts. Here, this is where it's acting as an open switch. So we're going to see that voltage now from the supply. We'll see that peak across the diode. So this is what the diode, that VRRM, has to be rated. It has to be able to see this peak when it's acting as a open switch or reverse bias. Okay, that's that limitation of voltage that we need to show. So basically, if it's not going to the load, it's across the diode. This one's across the load, so there's nothing at the diode. This one, the load's seeing here nothing because it's sitting there at the diode waiting to go across, but it can't because it's reverse bias. Okay, what it says here, according to Kirchhoff's voltage law, Vxy plus Vyz must equal Vxz. What does that mean? Basically is comparing the voltage across the diode and the load should add up to the supply. So if it's not at the load, it's got to be at the diode, okay? Because we have to have the same supply splitting across the two sections of the circuit. So the half-wave rectifier splits the AC waveform into positive and negative half cycles that when added together equal the input voltage. So this guy and this guy equal this. A DC voltage is usually expressed as an average value. The average voltage value of the output of a single-phase half-wave rectifier is 31.8% of the peak. So the equation for this value is 1 over pi. Okay, I put 3.14 there just because I don't know if I could find a pi button, but it says this in your module too. Okay, it's 1 over pi. Whatever's easiest for you to remember, if it's 1 over pi that's easy for you to remember, or this percentage, I tend to remember the percentages, but it's up to you. So the VDC, the volts DC, is our expected DC output of this AC supply when I'm using single-phase half-wave rectification. So the first step we have to do is find the peak, then we times it by that percentage to see what the output is. So for this one here, this is where we get back. Okay, so I'll just kind of show you this in the module. I think I normally do this on the board here. But we have to find the peak of the supply. Again, there's no values in this one that they've given to us, but because they haven't given us an AC supply. Say it was 120 though here. You would have to find the peak of 120. That would be your first step. So 120 divided by 0.707, and get that 169 point something rather peak. Then multiply that times the 0.318, and that's what your expected VDC is, okay, your DC output. And we can see that if this peak, let's say, is 169 volts right here, and that's what it would be here, 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 that's what the VRM rating of the diode has to be, because that's what the diode's going to see, is that peak voltage here. The other thing is to show that this is what the load is seeing. It's seeing a peak of 169 volts for basically one alternation, then it's seeing 0 volts, then a peak of 169. So that's why we're having to multiply it by this 31.8%. It's 31.8% of the peak, and it's going to give you an average across the load that's kind of down here. Okay, not a very high value of DC, but that makes sense because we're lacking a full alternation. Okay, the next one we talk about are the single-phase half-wave rectifier connected to L1 and N of the supply. Okay, so we have a kind of like an Edison 3-wire scenario here with our center tap. So we have L1, L2, and our neutral right in the center. So we have 120, 240 supplies. So 120 between L1 and neutral, and L2 and neutral, and then 240 from L1 to L2. Our load is hooked up from L1 to N, so that will tell me that my voltage expected would be the 120 volts because I'm not hooked up to L2. Okay, so this load is hooked across the 120 volt supply section of this transformer. And lo and behold, we have a diode in here too to help this load see DC instead of AC. So again, to calculate the average DC load, first what we want to do is calculate the peak. Okay, so in this case, they did give us a voltage here. So it's same as that single phase half wave. Oh, sorry, this is the one they just show half wave rectifier. Yeah, they are just showing that it's connected to one supply. So here's the math on that one that I was waiting to see. So you take your peak after you take the sine of 45, which is 707, or again, you can use root 2. This method too, you're going to get the same answer. Again, I stick to this method because it's familiar to me. I like to use the sine of 45 in case I need to find another instantaneous value. So I don't use this, but whatever's easiest for you. So again, the first thing we got to do, find that peak. Then we're going to times that by the percentage. And this is what we get as an output voltage. So even though we have a peak of 169 coming through on every other alternation, by the time we add it at that percentage there, we're going to see this is the expected DC output. So that load is going to see 53.9 volts DC to the load. The load frequency, the pulsating DC voltage at load has a ripple frequency. The ripple frequency of the output voltage of a single phase half wave is the same as the frequency of the supply. Okay, so we do have, if I have 60 hertz in, I will have 60 hertz out as well too for the ripple DC. Okay, so here's the center tap full wave. So I got a little bit ahead of myself there. I apologize. This is still a center tap scenario, but they were just kind of showing you how to do the single phase full wave. So a center tap transformer with 2 diodes means that the load sees voltage during both alternations. Okay, so now we're a center tap full wave rectifier instead of a half wave. So even if we're thinking, if we go back to this picture here, the reason it's half wave is because we're literally only seeing half of this sine wave. So if I'm in full wave, I would expect to see the full wave across the load. So potentially I'm now, instead of blocking this, I'm going to be able to flip it up and actually see that second alternation. So that's what we're going to see in this center tap scenario. So a center tap transformer with 2 diodes means that the load sees a voltage during both alternations. This is called full wave rectification. The figure below shows how full wave rectification can be accomplished with a center tap full wave rectifier. So different than the one that we saw earlier where we just had one diode in with the load and we didn't have anything hooked up to L2, and in this scenario would be L1, L2 neutral here. So what we have then is 2 diodes now. In the first alternation, this diode is going to be forward biased and this diode is going to be reverse biased, okay, just the way that it is put in the circuit. So when I see the D1 with this polarity at where the positive is at A and the negative is at B, okay, and then D is negative with respect to A. So as we're going through this first one, if we put a positive here and a negative here, we will see D1 is forward biased, so we will see this alternation come through for D1. And we don't see anything coming through here because D2 is reverse biased. Now on the second alternation, again our polarity switches, so now what was positive here is now negative. So now D1 is reverse biased, but D2 is forward biased, okay, because now the positive's here and the negative is here with respect to this positive. So in the first alternation, I have this portion of the circuit allowing the alternation through. On the second alternation, when the polarity changes, now I have this portion of the circuit. So D1 is conducting in the first alternation, D2 is conducting in the second alternation. So what that allows us to do is show that we will have the full alternations coming through. So we're not blocking this one anymore because we have that second diode that's going to conduct in that second alternation. So instead of having no voltage here, we do see a voltage here. Okay. Now, when it's saying here, the figure shows the waveform of the supply and load voltage. The conversion factor for a single phase full wave rectifier is 0.637 of the peak of the rectifier voltage. The average DC voltage output is 63.7, okay, which is literally double what we saw for the half wave. Okay, so the equation again for this value to get this percentage is 2 divided by pi. So again, it talks about that in your module. If you want to use that, by all means. Again, I remember the percentages, but whatever speaks to you. So calculate the average output of the full wave, single phase, full wave rectifier as follows. So we will show that we have, we'll get into the calculations again later, but we would get this, if we had a value here, we would find the peak of it times by 0.637, and then we would get the expected DC output. Okay, and it's saying here VXD is half of the AB peak. Again, if it's at like 0.637, so yeah, a little bit more than half, I guess. I don't know if that's what it's getting at here. But yeah, the important thing is that we're showing that it's definitely getting this alternation through to our load as well too. So we can also see that with this alternation coming through now, that our expected output to the load would be higher, because in our half wave we would see a peak, then no volts, then a peak, or then no volts. We want to be able, basically be able to say in our heads, well, it's going to have more voltage to the load because I'm actually seeing voltage on that second alternation now. Okay, so that should help in your head have an understanding that when we go through and have full wave instead of half wave, our expected DC output should be higher. Twice that of the half wave, in fact. So average DC output, we'll get into some calculations here to show this. So the transformer below has a 2-to-1 ratio, 480 volt, 60 hertz supply. Determine the average load voltage and its ripple frequency. Use the transformer ratio to determine the full secondary voltage. Use RMS values unless stated otherwise. So what that's saying is this 480 supply, that's an RMS value. If our 2-to-1 ratio is applied, that means I have 240 volts RMS from L1 to L2, okay, because of this ratio here. From L1 to N, I'm going to see half of this voltage, or 120. Okay, again, an RMS value there. So line 1 to N is 120 volts, and that's where the load is hooked up. Okay, so the load is not hooked up across the 240, it's hooked up across the 120. It's going from L1 to N. And then the diode configuration is the same, just a different drawing as this scenario here. Okay, so what we got to do then, knowing that the load is hooked up to 120 volts, we find the peak of what the load is seeing, which is 169.7 volts. Then we're going to find out that when it does it on the second alternation, it's also going to see that. So the load only sees half the secondary voltage on the second alternation when the other diode becomes forward biased and the first diode becomes reverse biased. Again, so we're going to see that second peak this time. So the load sees two peaks as if it was connected to two half-wave rectifiers. So calculate the DC average. So instead of the 318, we're going to use 0.637. And our output voltage literally doubled from this first scenario where we had 53.9 volts, so almost 54 volts. Now our output is going to be 108. So by having full wave rectification, we're literally doubling our output. Okay, and we're closer to, here's the 169.7 volts peak. We're closer to that than we were. We're sitting at about 108 volts. Again, not quite 100% of that peak, obviously, because we're still averaging it, because we're seeing peaks and valleys as we go through. So the load frequency, figure 7 shows the time for one cycle of the load voltage is half the time for one cycle of the supply voltage. Therefore, the ripple frequency of the load voltage is 2 times the frequency of the supply, or 120 hertz. Remember, your meter will count positive alternations only. Frequency is defined, so this is important here. Frequency is defined as the rate at which something occurs or is repeated over a particular period of time or a given sample. So what that means is a cycle is when something starts to repeat. So when we have our sine wave, the cycle doesn't start again until I hit here and it starts peaking again. Then it's repeating. So in this period, okay, the same in this time frame, I have one cycle. Well, when I do my rectification, I see now that this is what's going to the load. Okay, so for XD, that's the load right here. And here it is repeating again. So this is a cycle right here because this is repeating exactly what this is. So in the same time frame, I get twice as many cycles as I did with the original. So that's why we're saying that the frequency output for the ripple is double of what the supply is, because I have basically the cycle repeating itself here within the same time frame that I used to just see one cycle, I see two now. Okay. Again, the diodes must block the entire transformer secondary voltage when reverse bias. So when we talk about being reverse bias, that's when the diode is an open switch. It sees voltage across there. Okay. And when we talked about that for our single phase half wave, we saw peak across here. So we just want to make sure what peak are we seeing when this is actually in the open position. So each diode carries the entire load current half of the time. This means that the average diode current is half the average load current. Okay, so in regards to the VRM, that's voltage. This is saying, well, this diode is only conducting half the time. This D1 conducts for the first alternation, D2 for the second. So what they're saying is that if I got 100 amps going through here, it only has to be rated to carry half the current because it's only on half the time. Now, don't get confused by the fact that when it's on, yes, it is conducting the full load current. So if it was 100 amps, this is conducting 100 amps. But because it's conducting 0 amps in the next alternation, it averages out to half. And again, we got to remember that these are a snapshot in time. This sine wave is again 60 cycles per second. So it looks like this thing would actually see only half the current because it's only on for half the time. Okay, do have to be careful with that VRM too. Okay, to finish what I was talking about there is if this is my diode here, I see line B right here when this is well, let's look at this one because they're showing it as an open switch. So line A here, so that's 120 volts. This is the neutral point. D is, okay, not X. This D is the neutral point. So if this is an open switch here, I have A sitting right here. If B is conducting, that means I have B, which is also 120 volts, a different leg, coming through here. Well, then 120 volts is sitting here and my neutral is here. So B is sitting right here. So I have A on this side of the switch, which is 120 volts, B on this side of the switch, which is 120 volts. So this open switch here, or diode 1 in a reverse bias scenario, is seeing 240 volts RMS. So we'd have to find out what the peak is of that 240 volts to see what the VRM rating is for that. So if I take my 240 divided by 0.707, I get 339.46 volts. So this diode has to be able to handle 340 or 339.46 volts when it's reverse biased. If the rating is only 240, that thing is going to get destroyed as soon as it sees that higher voltage. Okay, so that's important. When this is reverse bias, it sees the full secondary, so not just half. Okay, we got lots of questions to get you through that scenario, so you'll be good at it whether you like it or not. Now, the last single phase one we're going to talk about is the full wave bridge. This is the most commonly used single phase rectifier. Uses 4 diodes. Shows below the 2 schematic diagrams for the same rectifier. Okay, so it's nice that we got some options here because this is exactly the same as this. Just again, comfortability, whether you this makes more sense or this. Potentially right now, neither of them do. But we'll go through these and show you how they're the same and basically how they're going through and what's going to the load at what time. So in this rectifier, A is positive with respect to B during the first alternation. Okay, so here's my A from my supply, here's my B, same scenario here, A here. and B here. So when we go through, I'm going to look at this one here first and show how this is going through on this first alternation. So the first alternation, again, if A is positive, what it's doing is putting a positive here on this diode, then the other side would be negative with respect to that. So D1 is forward biased at this time. So it's coming through here. Okay, the positive, again, if we were looking at the supply only at this diode, here's my negative coming here. This would be my positive with respect to this negative. So D3 is reverse biased. So I have a path through D1 to my load. Okay, again, we're not going to go down to D3. Again, this technically could be highlighted yellow, of course, but we're not going through here because this is reverse biased. On the other side, on the return, again, we just want to look at which diodes are forward biased and which are reverse biased. Well, if I bring this negative across, it's going to be a negative here and a positive here, so D2 becomes forward biased. When I look at this is confusing because I didn't jump it here, but this is connected to the positive, and then this would be negative with respect to that. So D4 is reverse biased. So right now I'm going through the supply. This again is for the first alternation of the cycle. I'm going to go through D1, through the load, and then back through D2 because it's forward biased to the other side of the supply. So the load will see that first alternation, and it's going to see it through D1 and D2. Those are the ones that are forward biased. Those are the ones that are conducting in the first alternation. D3 and D4 are reverse biased, so they are not conducting. Okay, so the current through the load is from C to D. Okay, so C is positive with respect to D. So that's what it's saying, positive here with respect to D. So now we look at the other alternation, the second alternation. So to compare, here was positive here, negative here now. So now we kind of look at, I go back this way, start at the positive, again, conventional flow for these ILMs, just to switch it up on you guys. So I come through here, again, I'm marking polarity, so positive here, because that's my positive, then negative with respect to that. So this is forward biased, this guy is reverse biased coming through, so I can get to the load through D3. Then on the return, my negative, again, carrying it through, here's your negative here, so again, positive with respect to that. And this guy, so now D4 is forward biased. So when I come back through and D1 is negative here, so if I carry that negative through, coming through here, D1 is reverse bias, so I can't go back up this way either. So when I'm coming through in this, I got positive coming through here, through D3, because it's forward biased to the load, and then back to my supply through D4 because it's forward biased. So that's my path for current to flow to the load, again in the second alternation. Thing to look at though too is that the current through the load is from C to D, so that C is positive with respect to D, just as it was in the first alternation. So what it's saying is my load is seeing the same polarity. So it saw positive here on C and negative on D on the first alternation, and then saw it again, positive on C, negative on D in the second. So what that's telling me is my load is seeing direct current. Okay, so it's not seeing alternating anymore. So I had alternating current coming in, and my output through this full wave bridge rectifier, single phase, is going to be DC to my load. Again, I'm seeing this full wave during for one cycle, for one period, so the same time frame. Now I see my DC output, this CD that we saw, that's this CD, so that's my load. Now my load is going to see this alternation, which is this guy right here, and this alternation, which is this one, basically flipped up. So again, if we look at the definition of cycle is when something repeats, well, this starts to repeat right here because this is the exact same as this first one. So now I have two cycles in the same period where I had one cycle. So basically I would double my frequency again for the full wave bridge. So here's another scenario of how it could be hooked up. Again, wiring diagram just different. You still have to follow the polarity. Okay, this one is a 2 to 1. So basically what it's saying is we have our RMS of 480, 2 to 1. So we'd see 240 across L1 and L2 and don't have anything hooked to the neutral in this scenario. So my 240 is what the load is going to see. But again, we have to find the peak first because that's this value. So that's what's actually going to go through the rectifier and to the load is the peak value. Again, but now we're at that same percentage, that 637, because we are full wave single phase. So I take that peak voltage, times it by the percentage, or again, you can use pi, whichever tickles your fancy. Then you can see your expected DC output to your load. So this is what the load is going to see, a DC voltage of 216 volts when we had a 240 volt AC supply into our single phase full wave bridge rectifier. Again, the frequency, ripple frequency to the load 2 times, okay, just because like this we saw it. Okay, we're doubling the frequency or doubling however many cycles we see in the same period that we saw for our supply. So load and diode current. Again, we mentioned this a bit, the fact that the diodes are only on for a certain amount of time. So you can also determine the load that each diode has to carry. If the load has a resistance of 10 ohms, calculate the current for each diode. First, calculate the average load current as follows. So I'm going to take my VDC, okay, in this example, which I think is right out of your module, so don't try to relate it back. I don't, to be honest with you, it's definitely not this voltage, so I'm at a loss here where this voltage is coming from, but let's just look at this based on the voltage given to us. So 187 volts divided by 10 gives me a current of 18.7 amps. Again, if this is a DC voltage here, VDC, this is going to be what my current is for my DC load. Now, since each diode carries the load again only half the time, the average current through the diode is calculated as follows. So it's basically half. So even in this scenario, these diodes, go back to this part, 2 are conducting at the same time, and then 2 are off at the same time. In this, these 2 are on. So D1 and D2 are on, then in the next alternation, they're off. D3 and D4 are off, now they're on. Okay, so they're only on, again, half the time. So that's where we're getting the average again. When they're on, they do see this full current. But because they're also off for the next alternation, we're going to average it out. So that's why they only see half. So they only have to be rated for half as well. Bridge rectifier modules, okay, so you can buy these obviously pre-made. They have the 4 leads, again, each lead coming in. You got your AC here coming in as your input, and then your DC output. So you would bring your, in the previous example, 240 volts AC here, and then what we would get on our output would be that calculated value of 216. So I'd see 216 at these DC, and this is what would go to my DC load. Okay, so I'm just gonna, what are we at here? Oh, dang, 30 minutes. So I'm gonna go through 3-phase here, and then I'll stop for battery chargers. So again, now we're into 3-phase rectifiers. So we have a 3-phase half wave and a 3-phase full wave. So the first one we're going to talk about is half. So these are used for some power circuits. The figure below shows the connection of the diodes required for a 3-phase half wave rectifier. A neutral conductor is required, so a 4-wire connection source must be used. Okay, so we do have a neutral for our half wave. We have diodes here from our line A, B, C, and then whatever one is peaking at the time is the one that's going to go through to the load. This figure here compares the input from a 3-phase supply and the output voltage waveforms for a 3-phase half wave. The diodes are reverse biased during the negative portion of the cycle. So when they're down here, they're reverse biased. Okay, and only allow the positive alternations. So here's my positive V to A VAN. So that's this bump right here. That's when diode 1 is forward biased. Diode 2 is forward biased when BN is peaking. And then diode 3 is forward biased when CN is peaking. So this is what my load is going to see. We're not seeing these negative alternations, so that's why it's 3-phase half wave. We're only seeing the positive alternation. Okay, and now we're seeing we have 3 cycles in the same period that we saw 1 in. Okay, so that's a prelude into what we talk about here. So calculate the average voltage across the load if connected to a 3-phase half-wave rectifier using the following calculations. So again, we're going to find the peak of the phase voltage, not line voltage, and we're going to multiply by this 0.827. Okay, so I think this is the first time when they don't give you a pi to use. So you just have to remember that. I do have a way that they found that, but it's very convoluted, so just remember the percentage. If the 3-phase supply of the circuit below is 122.08, calculate the average load, voltage, and the ripple frequency. So the load sees peak phase voltage. So my phase is 120. I'm going to find the peak of that, again, because the load is hooked to neutral, so it's just seeing phase. I get the peak of 169.7 times it by our percentage, and this is what the load is going to see, 140 volts DC average. Load frequency, again, we can basically show, we did earlier here, that it's going to be 3 times the supply, okay, because we have 3 cycles in the same period. So that's what this is saying, 3 times the frequency of the supply. So 60 hertz times 3, so this would be the frequency of the ripple DC output. Load and diode current. Using the same rectifier as the previous problem, calculate the average diode current when the load resistance is 10 ohms. Okay, so this one we're going to use our VDC average. We're going to get our current based on that. And now again, these are only conducting 1/3 of the time. And we saw that here, kind of right here. So D1 is conducting, then 2, then 3. So while 2 and 3 are on, while D1 is on, 2 or 3 are off or reverse bias. While D2 is forward, D1 and D3 are reversed. So they're only conducting 1/3 of the time. So when we go to do our current, we just take that load current based on our VDC and we divide it by 3. And that's what each diode will see. Here's a little blurb here that means a lot. VRRM is V peak of the line voltage. So that reverse repetitive maximum, that's what the diode sees when it's reverse biased, again, like an open switch. But it doesn't see the phase voltage, it sees the line voltage. Okay, and the way I look at that is, when I think of, let's just look at D1 is conducting right now. Okay, if D1 is forward biased, D2, this is an open switch, this is an open switch. So I'm carrying phase A down here. So phase A is right here. And the load is seeing, right now it's going to see an alternation from A and N. Okay, but that also means that phase A, so phase A is here, coming down through here, it's also here, and it's also here. So across each diode, this one's going to have phase B on one side, phase A on the other. That's line voltage. Okay, and this one's going to say C and A. Again, line voltage on either side, and 2 different legs. So you're going to see 208 RMS across these. So you'd have to find the peak of 208. That's what the VRM would have to be for those diodes. 3-phase full wave, again, very similar. Just now we're going to see those negative alternations coming through. A neutral conductor not required because we've got the load hooked across the line instead. So we could use Y or delta. Figure compares the input of a 3-phase supply and the output voltage waveforms. So again, in the same period to see these 3 separate phases peaking, in the same period I see 1, 2, 3, 4, 5, 6, because now we're seeing positive and negative alternation, positive, and negative. So we're seeing 6 cycles in the same period. For example, if the 3-phase circuit below is 122.08, calculate the average load and ripple frequency. So on this one, again, there's no neutral. So what we're going to use is 208. That's what the load. So we got to find the peak of that, which is 294. And then we're going to use this percentage. Again, there is a bias, associated with that. Or you can just remember that. But it's showing us here, we're seeing 95.5% of the peak to our load. So significant amount of voltage, almost the peak. Again, only 4.5% difference. So this is what the load is going to see. And again, now 6 times the frequency. So we're going to see 360 hertz on our ripple. Again, VRM, peak of the line. So that's what those diodes have to be rated for when they're reverse biased. They're going to see line 1 and line 2 potentially across them, or line 1 and line 3. So the peak of the line is what they have to be rated for. And then you get three-phase full-wave rectifier modules. Again, you're going to have our supply coming in, red, black, blue, and then our DC output. Okay, so then we'll talk about battery chargers after.